Hey everyone, in this video I want to talk about special right triangles. So what I'd like to do is just talk about where these formulas come from, and I want to use them in a couple examples. So to begin with, there are two types of special right triangles. One of them is a 45-45-90 triangle, and the other one is a 30-60-90. In both cases, the naming of the triangle refers to the angle measures within that triangle. So a 45-45-90 triangle has two angles that are 45 degrees and one angle that's 90 degrees. And then for 30-60-90, same idea. It has a 30 degree angle, a 60 degree angle, and a 90 degree angle. So to see where these come from, we're going to refer to a couple of shapes that we already know. So the first one, we're going to be taking a look at a square. Now if I take this square and I draw in one of the diagonals, we end up with two triangles. So drawing in that diagonal, we get this like so. And then we already know that a square has four right angles. And drawing in that diagonal actually splits these other two angles directly in half. So these two angles are 45 degrees. So taking a square, splitting it up into two triangles, we end up with two 45-45-90 triangles. Now, this is a special right triangle, and that means that the side lengths have a special ratio about them. So just to show you what I mean, let's think about a couple examples. So let's say the side length of my square, or the two legs of one of these 45-45-90 triangles, let's say that this has a length of 3. And now I want to find the length of the hypotenuse. I could use the Pythagorean theorem. So let's label that as x. 3 squared plus 3 squared is equal to x squared. So that's 9 plus 9 is equal to x squared. So we end up with x squared is equal to 18. Taking the square root of both sides, we get the square root of 18. Now, this radical I can simplify. So simplifying radicals, what we need to think about is what is the biggest perfect square that 18 can be divided by. In this case, it's going to be 9. So this is equivalent to the square root of 9 times the square root of 2, because 9 times 2 gives me 18. So that means my hypotenuse is 3 square roots of 2. The square root of 9 gives me 3. The square root of 2 has to stay as is. All right, so now let's think about just one more example and see if we can notice a pattern. So now let's think about, let's say these have a length of 5. So doing the same thing, 5 squared plus 5 squared is equal to x squared. This is going to be 25 plus 25. So we get x squared is equal to 50. Taking the square root, x is equal to the square root of 50. And again, we can simplify this. So if we simplify, what's the biggest perfect square that goes into 50? It's 25. So we can take 50, split it up into the square root of 25 and the square root of 2. And now we can finish simplifying. The square root of 25 is 5, and the square root of 2 has to stay the same. Now if I look at my two solutions I got here, 3 times the square root of 2 and 5 times the square root of 2. They both have a square root of 2 in them. Also, if I take a look at the coefficient that's in front of that, 3, that was the side length that we used to begin with, and 5, same thing. So now we can generalize this. So let's just say, for simplicity's sake, let's say the sides are 1. If the two side lengths are 1, then my hypotenuse has to be the square root of 2. So the ratio is 1 to 1 to the square root of 2. So that means that this is an isosceles triangle. The two legs are the same. And then the hypotenuse is the leg times the square root of 2. So if my side lengths were 10, then my hypotenuse would be 10 square roots of 2. If they were 100, then the hypotenuse would be 100 square roots of 2. So if I wanted to write this out in some variables, I could say that if my legs are x, some variable, the two legs have to be the same, and then my hypotenuse is whatever that leg is times the square root of 2. So that's a 45, 45, 90. Now, for the second special right triangle, 30, 60, 90, we're going to start with an equilateral triangle. And what we're going to do is we're going to drop in an altitude of this equilateral triangle. So dropping that straight down, we get a right angle like this. In an equilateral triangle, we know that all the angles are 60 degrees. And then with this altitude, it's going to split this angle up here in half. So that means that this is 30 degrees. And that gives us our 30, 60, 90. Now, let's say the side lengths of our equilateral triangle, let's say that this was 2, for example. When I drop in that altitude, it takes this other side and splits it right in half. So if that's the case, then this side length of the triangle, from the vertex here to where this altitude is, that's going to be half of 2, which is 1. And then we can use the Pythagorean theorem to figure out our missing side. So 1 squared plus x squared is equal to 2 squared, which is 4. But I will write everything out here. So this is 2 squared. So 1 plus x squared is equal to 4. So that means x squared is equal to 3. And we get x is equal to the square root of 3. And if we were going to do some other examples, we would notice a very similar pattern to what we had for the 45, 45, 90. So this is the square root of 3. So that's our special ratio for this triangle. It's 1 to the square root of 3 to 2. So what that means is in a 30, 60, 90, I normally base it on whatever the shortest side is. So if I know that this has a length of 1, the hypotenuse of that triangle is twice as big, so 2. And then the longer leg, the side that's across from the 60-degree angle, is the square root of 3. So just to show you what I mean by that, so let me get rid of these side lengths. So let's say that our short leg, let's say this has a length of 100. Then our hypotenuse has to be twice as big as that. So this has to be 200. And then the longer leg, the side that's across from the 60-degree angle, is going to be this short side times the square root of 3. So we can write these down in variables. So for our 45, 45, 90, it's a ratio of x to x times the square root of 2. And then for our 30, 60, 90, we have x times the square root of 3, and 2x. So that's what makes these special right triangles, because they have this special ratio of their side lengths. So now that I showed you where this comes from, let me just talk through a couple quick examples on how to use this. So in this first one, I want to find the value of x in each of these triangles. Now taking a look, both of these are isosceles right triangles. So that means that these are 45, 45, 90. So these two angles are the same, so they have to be 45 degrees. So because the side lengths are the same, the angles that are across of them also have to be the same. So we have 45, 45, 90 triangles. So in letter A, I know the leg, so it's 22 units long. So if I want to find the hypotenuse, all I have to do is take 22, multiply it by the square root of 2, and that's it. There's my answer. Now let's say you did forget this shortcut. Let's say you forgot the rule for 45, 45, 90. You could also come to the same conclusion by using the Pythagorean theorem. 22 squared plus 22 squared, set that equal to h squared, and when you solve it and simplify, you would end up with the same thing. Now in letter B, if I compare that, now we want to find out the leg instead of the hypotenuse. Over here, we took 22, multiplied by the square root of 2 to get the hypotenuse. So in this one, in letter B, I actually want to go backwards. So I want to take 10 times the square root of 2, and now instead of multiplying, we're going to divide by the square root of 2. So the square root of 2 and the square root of 2 will simplify. So that means that our legs, the two legs of this triangle, are 10. So as you can see, because of this special ratio of the side lengths, we're able to make pretty quick work of these two examples. All right, let's take a look at my last example. It says find the values of x and y in the diagram. So we have a 30, 60, 90. So remember the ratio is x times the square root of 3, and then 2x. So x, this is the shortest side, the side that's across from the 30-degree angle. The short side times the square root of 3, that gives me the side that's across from the 60-degree angle. That is the longer leg. And then 2 times that short side, that gives me the hypotenuse. So in my example here, y is the hypotenuse. So I already know that y is just going to be twice as big as whatever x is. But I need to find x first. So normally what I would do is I would take this short side and I would multiply it by the square root of 3 to get the longer leg, the side that's across from the 60. So because we're thinking a little backwards, I actually want to take that longer leg, so 9, and then I want to divide that by the square root of 3. That's going to give me my shorter side. This is written in a little bit of an improper form, so let's rationalize the denominator by multiplying the top and the bottom by the square root of 3. So we get 9 times the square root of 3 over 3, because the square root of 3 times itself is 3. And then we can simplify 9 divided by 3, so we get 3 times the square root of 3. So that's what x is here. So the short side, the short leg of this triangle, 3 times the square root of 3. And now that we know that, all the hard work is done, because we already know that the hypotenuse, or y, is just going to be twice as big as that. So if I take 3 times the square root of 3 and I double it, y is 6 times the square root of 3. So there's our two answers. So hopefully you can see here that the special right triangles, they have a special ratio of side lengths, which gives us a nice shortcut that we can use. But it's also important to remember that this is just a shortcut and not always necessary. So we still can just use the Pythagorean theorem to help us find our answers, but as you can see in examples like this and the previous ones, knowing the special ratio does make these pretty quick, and we can find our answers very simply.